Je suis enchanté d'accueillir Sylvain CALINON ici à Montréal virtuellement. Il est chercheur principal à l'Institut de recherche IDIAP à Martigny, en Suisse, et chargé de cours à l'École polytechnique fédérale de Lausanne, EPFL. Il dirige le groupe, et là je peux le dire en anglais, parce que Sylvain, est-ce que le nom est vraiment en anglais?
Il y a les deux, il y a aussi Institut de recherche IDIAP.
Ah, et puis, même parce que j'ai Robot Learning and Interaction à IDIAP.
Alors celui-là, c'est vrai qu'il n'y a que la version anglaise.
Ok, d'accord. Avec son expertise est en collaboration humain-robot, apprentissage robotique par démonstration et optimisation basé sur des modèles. Son travail se concentre sur les applications robotiques centrées sur l'humain, où les robots acquièrent de nouvelles compétences à partir de quelques démonstrations. Nous autres aussi, on est capable de faire ça grâce à un système neurologique qui s'appelle les neurones miroirs. Euh, il développe des modèles qui exploitent exploitent efficacement la structure et la géométrie des données. Ça va m'intéresser non seulement la géométrie des données avec lesquelles tripotent les robots, mais aussi les choses dans le monde que rencontre le robot dans la vie quotidienne. Le titre est Apprentissage robotique par démonstration. Le résumé, vous connaissez déjà. Et avec ça, j'invite Sylvain à prendre le volant. Bienvenue à
Très
Montréal.
bien, merci beaucoup. Merci pour l'invitation. Donc je vais faire cette présentation en anglais. Vous pouvez m'interrompre à n'importe quel moment pour des questions, puis vous pouvez poser des questions en anglais ou en français. So I'm Sylvain Calinon. I come from from the IDIAP Research Institute. It's a research institute in the Swiss Alps, in Martigny, in the region of Valais. We are about 200 persons working in the field of machine learning and artificial intelligence. The institute has been created in 1991, so we have seen different waves of AI. So initially, the name was actually with the acronym IA for intelligence artificielle. And when AI was not popular anymore, we dropped the acronym, and now we are sometimes putting it back again. Now that we are talking a lot about this artificial intelligence. But the core of the developments that we do at IDIAP and the core of the research is related to learning applications, like how to acquire skills in different domains and for different applications. And we have a link with EPFL, École Polytechnique Fédérale de Lausanne. We have a joint development plan with them, meaning that our PhD students have the two affiliations with IDIAP and EPFL, and we're also doing some teaching on our side at EPFL. So IDIAP exists for more than 30 years, and I arrived at IDIAP 12 years ago, and I'm heading a group called Robot Learning and Interaction. This group is about transferring skills to robots. So we're interested in mechanisms so that we can fluently transfer new manipulation tasks to robots. And compared to other groups, we care a lot about the frugal aspect in the learning, in this learning component. So we are talking about frugal learning as a way to describe what we would like to transfer this skill with a minimum number of data. So ideally, we would like to use just a few demonstrations in order to have these robots being able to replicate what we have demonstrated with this small number of demonstrations. Frugality also means different things. It means that we would like to limit what really needs to be learned, because there is an aspect of robotics that I don't like so much, is that it's tempting to put everything as a learning problem, because robotics is a very multidisciplinary field and we need to know a lot of engineering techniques in order to have these robots being able to move in the real world. We need to know about signal processing. We need to know about control theory. We need to know about planning. We need to know about perception. So it's a lot of different technological aspects that we would require if we would like a robot to be able to perform all of these skills on its own. So it's very tempting to reframe that as a learning problem. But in our group, we are really considering what should be learned and what we can put in a robot as prior knowledge about the world, about the movement, about physics, about gravity. So we try to find the right balance between models that we already provide to the machine and data that will be used by the robot in order to fill the gap with what we cannot teach efficiently to the robot. So we will use this term frugality I will use this term in my presentation. Now, I will start this presentation by first showing you a few experiments that we are doing in our group, just to give you an idea about what kind of tasks we are talking about. So I will start with a few videos, not explaining what's behind, but just so that you can get an idea about what we mean by manipulation tasks. So first, we often use two robots. So we would like to have bimanual capability, a bit in the same way as a humanoid would have two arms and can use these two arms in order to move large and bulky objects. We would like also to have robots using tools and understanding not only when to use these tools, but also how to use these tools. So typically, how to grab the tool so that it can be used efficiently. And depending on the task, we might have different affordances, and sometimes the same object, the same tool, might be grasped in different ways, depending on what we want to do out of this tool. So for example, if I have some tool here that I can use to grab objects that would be too far away from the robot to be reached with its gripper, then here it will use the tool in one way. But if we have another task that is maybe to put back this tool in a shelf, then it can be grasped in a different way. So the goal is also to understand and learn how to use efficiently these different objects and tools. Then we are also interested in non-prehensile manipulation. So, you know, when we talk about a robot manipulating objects, we often think of grasping, of gripping the object, but we have a lot of skills that do not directly involve the hand, but that are more about exploiting the environment around the robot so that objects can be pushed, can be pulled. And this is required if we want to first extend the workspace of the robot, because by pushing objects, we can reach actually larger portions of the space. It can be used to separate objects, which is very useful if we have a stack of objects and we would like to isolate an object so that it can be grasped more efficiently. It can be used also to better perceive the scene. So if we have a video camera observing the scene, and if we have occlusion because of objects hiding other objects that would be behind, then pushing and pulling can also be used as a way to separate objects so that we can help the vision system to determine what are the locations of these objects. So here we are sometimes talking about active perception, where the robot can actually change the configurations of the objects in the environment in order to better locate them and to better manipulate them. And this pushing and pulling, it can be extended to other aspects of the environment. Here I'm giving the example of a box that we need to tilt in order to bring it to a desired configuration. So it's a task that we could do with two arms, but if we want to do it with only one arm, then we can exploit these different, we can exploit the physics and these different contact point that we have in the environment in order to change the configuration of the box. So in this case, to tilt it and to slide it so that it can be put in the desired configuration. And then non-prehensile manipulation is also about percussion, eating skills, like something more dynamics, where we have contact with the object, but in a very brief instant. And here it's in this video schematized by this arrow key playing game, and it's a challenge that is being organized in robotics and in AI conferences in order to see, like, we are competing with another robot, we don't know what the other robot will do, and the goal is to program the robot so that it can, as best as possible, anticipate what the other robot will do, and understand its strategy, on observing the game and getting to know what to do in order to win the game. I have also like other examples of non-prehensile manipulation that is involving tasks that are even more dynamics. Here I'm giving the example of a throwing and catching task. Here to flip a pancake. A task being complicated to learn, especially if we want to learn this from demonstration. So later in my presentation, I will show the importance of combining different learning strategies so that we can also acquire this very dynamic task, and to see what's the role of the user, what's the role of the robot if we want to acquire such kind of dynamic skills. And since we are in Switzerland, we also have a lot of applications related to the watch manufacturing industry. So often we have industrial colleagues who are asking us to do very precise tasks. And sometimes it's complicated to do this very precise task. And here we need to really think of the problem of understanding what does it mean, precision. Because often if we think of us, when we do something precise, we use a lot of feedback. The same task, often we cannot do it blindly. We need to correct with some visual cues or tactile cues in order to become to be more precise. And with robots, we can do the same. So we can use sensors that can correct the movement. So even if the robot will be more precise than us, but we can even go beyond this precision if we are using a smart loop between the sensing and the motor control capability as a way to cope with errors and perturbations. This is also like a topic that we study in our group. So here I was talking about a robot that needs to produce something autonomously. But we have also a lot of applications that are involving both the user and the robot. So it can be broadly described as human-robot collaboration. It encapsulates a lot of robotics problems. If we think of prosthetic devices, it's a robot, but collaborating with the user. If we think about teleoperation, it's also another kind of collaboration where the user needs to teleoperate the distant robot. And if the teleoperation system is nicely done, it means that the user should feel as if the user was in the shoes of the robot. So ideally, we would like the user to not only to control the robot, but also to have some feedback about what the robot is doing. And here we have sometimes like systems, as in this project, that was involving a full exoskeleton that was used as a way for the user to feel immersed in a virtual environment and to do the task within this virtual environment. But on the other side, we have a robot actually doing the task remotely with a very distant robot in this case, because in this example, it's another robot that is executing the task. And here we have a lot of research questions regarding sensorimotor aspects, and here with delays, because we have a very large delay between this teleoperation center and the remote robot. So here we actually solve the problem by thinking of this as two different loops, if you wish, where we have a local loop that can correct very fast when there are perturbations, and another loop that is much slower and that is involving higher level components in the task. So here it means that we are decomposing, if you wish, like very low level reactive behaviors together with a higher level behavior where the user is controlling the robot remotely by providing components that are more symbolic, I would say, regarding the task. So typically, the user will tell to the system, there is this valve to be turned, and the user can decide if it's one valve or another. And locally, if there is a perturbation, the user doesn't need to know about this perturbation. The system will automatically adjust so that the system can cope with this perturbation without disturbing the user.
Sylvain,
It's
do you hear
reduced.
me? Can you hear me?
Yes, yes, yeah.
Can I ask a quick question
Of course, yes, yes, please.
to introduce the audience to the fact that you accepted some questions? Is your work in any way at all actually or intending to be neurally inspired in any of these tasks?
I would say, loosely speaking, yes, but I would say it's more about getting inspired. So it's not really like the mechanisms behind are not doesn't try to mimic what we really do. It's more that we observe what we need to do a task, and then we might mimic it without using the same mechanism. So it's like, I would say, very loosely inspired.
Thank you. If any particular examples of a neurally inspired successful function could occur to you, please draw it to our attention.
Okay, all right, yeah.
Thank you.
Yeah, so here what you see on this last video on the bottom right corner is a mapping problem. Like we have the robot on one side that needs to turn a set of valves, and on the other side we have the user. And the user is using one of the robot as the input device. So the user cares only about the robot that it can see. The user decides to turn valves, so we don't know in advance which valves have to be turned. And on the other side, the valves are placed differently. And in this video, it's showing in our lab how we emulate these complicated problems of an underwater robot, how we can test a mechanism that is more simple, because here it's involving two robots that are side by side. But you can still see with this video that there is this mapping problem, that the valves might be at different places, and we would still like to have something as a smooth system so that we don't have interruption in the task, and the user also doesn't need to care about this different placement of the valves. So the user cares only about what he sees, meaning that in terms of cognitive workload, it's much easier than having to care about the remote robot that has different configuration of valves. So that was an overview about what kind of experiments we consider in our group. Now I would like to
it's a good moment for me to ask you another pedagogic question. You have a very full slide there with 1, 2, 3, 4, 5, 6 things happening at the same time. Do you have any strategic advice to us where our eyes should be looking?
With the videos?
Yeah.
So yeah, they were run one after the other, but I will try to use the mouse pointer next time I show videos so that you see what I'm showing. Yeah. All right, yeah. So behind these experiments, we have learning from demonstration components. So it's one of the key technology that we use in our group. And by learning from demonstration, I mean going beyond some record and replay problem. So sometimes some of my colleagues, they think that we are just collecting a demonstration, like recording a movement, and later we are replaying the exact same movement. But in reality, learning from demonstration is much more than this. If we think of a robot that has to grab a box and to hold the box, then what we would like is to have this robot being able to adapt to new boxes. If I'm changing the locations of the boxes, if I'm changing the shapes of the boxes, then the robot has to understand what was the essential aspects of this task that needs to be replicated. And our goal will be to try to extract what are these essential information behind, so that we can have robots that can do meaningful movement if there is a change of boxes or if you change also the robot itself. So if we would like to buy another robot, and if we have our previous robot that has learned how to grab a box, then we would like our new robot that has new morphology to also be able to reuse this knowledge and to understand what are the spatial relationships and what are really like the essential aspects behind the movement, so that it can cope with perturbations and adapt to new situations. So the challenges behind learning from demonstration is really this generalization aspect and adaptability aspect. And the other main challenge is to know how to provide the demonstrations, because here I'm not really saying at the moment like how we provide these recordings of movements. So a first way to do this is to use cameras. It can be possibly with markers that we attach to the tools that we use, to the objects that we use. And these cameras can be here to record what we would like to record as movements of objects and movements of hands. So that's the first approach. It's sometimes called observational learning. The pros and cons of these techniques. So what is good is that the user doesn't need to care about the robot. The user is executing the task. What is bad is that when you do this, you might provide demonstrations that the robot cannot do. Like maybe you are doing a movement that is too fast for the robot. Maybe you are using too much space around yourself, and the robot maybe has a very limited workspace. So it might mean that maybe we are recording something that is very hard for the robot to do. So it has really these pros and cons. Like simple to implement. The user doesn't need to care about the robot itself, but with this disadvantage that we need to consider, that the mapping problem will be here more complicated. So that's one way, observational learning. Another way is to grab the robot by the hand and to show to the robot with its own body what to do. It's sometimes called kinesthetic teaching. Here you see this example with a dough rolling task, where we teach to the robot how to change the movement according to the shape of the dough. And here in this case, it was provided with this kinesthetic demonstration technique. And I will come back to this aspect as well later. I will have another demonstration also using kinesthetic teaching. Here, the advantage is that we demonstrate something that the robot can do because we use the robot's body to do the task. But it's more complicated to show this task because we need to consider both the task and the robot limitation. So it's not necessarily intuitive. Sometimes we don't know exactly where are the motors, how is the robot articulated. So it requires some practice by the user, but the user will be still quite good at doing this. So if you ask someone not knowing robotics to play with the robot for 2 minutes, then the person can already demonstrate some task to the robot. Another possible disadvantage, is that the user can control only a few degrees of freedom. So you have this articulated chain, but we have 2 hands, so we cannot move the whole robot. If it's an arm, as we see here, it's okay. But if it's a more complicated system, if it's a humanoid, and if you would like to move the 2 feet of a humanoid robot, then it's nearly impossible to demonstrate what it means to walk by just moving the feet with two hands. And if you have multiple persons doing it, it's becoming even more complicated because you need these persons to synchronize in order to demonstrate a task that is inherently coordinated. So it's also like not a very good way of using kinesthetic teaching. So that's, let's say, in a nutshell, what are the pros and cons of kinesthetic teaching. Here, something maybe that I should also mention is that the robot here is helping us when we do this. It's actually carrying its own weight. So from on a technological level, when we do this, the robot is controlled. So we are sending motor commands to the robot, and we ask the robot to compensate for its own weight. So we do it mathematically by knowing the different weights of the different body parts of the robot. So we know what kind of command we can send as force commands if we want to compensate for the effect of gravity. So it's a way to help this collaboration so that the user doesn't need to care about the weight of the robot. It only has to care that it has this limited workspace due to this articulated chain that we need to move in space. So maybe now a third way of demonstrating task is to do it through teleoperation. So here in this example, what you see is a user on the right demonstrating to the robot how to insert these different gears in order to perform this assembly task. The advantage of this teleoperation technique compared to kinesthetic teaching is that in this case, the user can also get feedback about the force. So when inserting the gears, you also demonstrate to the robot what to do when we are feeling resistance, what kind of force we need to use. So it's a way to demonstrate not only movements, not only positions, but also demonstrating really like a sensorimotor capability. So if we have like enough examples, then we can demonstrate what to do in different situations. And it's important for assembly tasks because sometimes there are things that are really small, like like when you are inserting these gears, sometimes it can get stuck. And visually, you don't see the difference, but it's only haptically that you can feel that there is a resistance and that you need maybe to apply more force or to try to redo the task once more. Don't hesitate to interrupt me if there are any question. I don't see you, so just use the microphone and interrupt me at any time in my presentation. Okay, yeah, something else that I didn't mention is that all of these demonstration modalities come also with the user interface aspect. So these are actually some forms of user interfaces that would try to mimic, broadly speaking, what we would do if we would take the arm of someone to demonstrate a task or use vision as a way to show to someone what the task is about. But we have also like other technologies, like we have like augmented reality interfaces, we have simulators, we have graphical user interfaces that we can use in complement of this. So another research topic to transfer skills is to also look at solutions that would be based on mobile phones, as in this example, or other kind of modalities that go beyond the standard interaction between two persons. And the goal is to know how to use efficiently these different techniques. This I will illustrate that with this example. So it's a learning example. You will see that these two robots will learn a very Swiss task that is to serve raclette cheese. And we did this video as a way to discuss about learning capabilities and the role of machine learning in robotics. So here it's like the promotional video that you see on this on the top right side, and on the bottom left corner I will explain what's behind. So what's behind is to exploit this kinesthetic teaching mechanism with someone who is not expert in robotics. So here in this case, it's someone who knows how to do this skill manually. And here the goal is to record what the person is doing. And what we will record is movement, but also force, and how this force will change with time. We also learn what to do when the cheese is melting, because demonstrations will not be the same depending on the size of the cheese. So depending on this 8, we will have different kind of offset in the movement. And the goal is to learn that, as well as this force component. And now the force component is varying in time. There is also something highly dynamic. So if you try to slow down the same movement, the task will not be replicated correctly. So it's also about understanding what's the dynamic behind. So in this kind of promotional video, it's already showing what kind of challenges we have as interface to demonstrate the task, but also at what needs to be recorded and what needs to be adapted to new situations. So learning is actually is more elaborated than a one-way process where we have the demonstrator and the imitator. It's more than this. It should be ideally in a loop. It should be more of an interaction. So that's something that we are also like I would say defending in our group, is that we talk too much about machine learning, but we should also talk about machine teaching, active learning, curriculum learning, in the sense that we should learn in a specific order. We would need to start with something simple and have examples that are more and more varied or more and more difficult. If we want to have a learning robot that can acquire skills more in a faster way. We need also to consider different learning strategies. So it's not only learning from demonstration, it's learning from demonstration combined with other learning strategies. If I'm giving the example of learning how to play football, then I cannot learn how to play football just by watching TV. It would be useless. Like watching demonstrations and not practicing would not work. I could try to learn a sport, maybe that I don't know about, on my own by trial and errors. If I would have the rules of the game, I could try on my own, but it would also not be ideal because I would not have models. I would not have like I would need to find my own way of doing the skill rather than relying on past experience of other persons who have maybe discovered tactics or ways to do the task in a better way. So often it's a combination of learning strategies that we need. And we need to orchestrate these different learning strategies, which is very difficult topic in robotics, like to understand this meta-learning problem of organizing these different strategies so that we can transfer a task to a robot. So it can be using learning from demonstration, it can be using reinforcement learning, that we can also call the learning by trial and error or self-refinement. Learning from demonstration also comes with many different flavors. Now we'll have a slide describing this just after, but we can think of the robot that needs to emulate the high-level goals. So it could be that the robot is understanding the goals and tries to replicate the goals. Or it can be a robot mimicking the actions. So not really trying to understand what's the goal behind, but copying the actions blindly in some way, and using these actions as a way to replicate the task. It can also be feedback. So here, in my own work, we are not doing this so much, but it's a very important aspect. It's to also understand how to exploit feedbacks. especially for the parts of the task that are symbolic and that can be where the robot and the user can communicate around this task. So when there is really like a symbolic meaning with a word that can be associated to it, then feedback through speech is an important aspect that needs to be considered. And finally, I'm using this term scaffolds. So scaffolds means that the user can also put the robot in a situation that is the ideal situation for the system to learn. So technically, what it can mean is to move objects. You know, if you need to teach a manipulation task to a robot, you can put the object first maybe in front of the robot at a location that is easy for the robot. If the robot has succeeded to grasp this object in the middle of its field of view, then what we can try next is to move the object a bit on the side to see if the robot can maybe use like other degrees of freedom as a way to reach this object. Or maybe we can make it even more complicated by hiding the object behind another one. And there is here like a situation that can be controlled by the user. So it's a bit like the user decides what's the training protocol for the system, what's the curriculum, so that the robot can progress in an efficient way. And this is something that is not easy to do. Like trying to automatize this is quite difficult because we do that naturally, so we don't realize that we have this teaching propensity that we know very well how to teach others because we are doing this socially and we are transferring skills socially in this way, and we even don't realize that it's something that is hard to put as a technology when we have a robot that needs to acquire new manipulation skills. So we tend to forget about this. It's easy for us, so we don't think it's complicated for a robot or for a system, for a learning system, more broadly speaking. So instead of talking about machine learning, I would prefer to talk about learning as a scaffolding process. And I like this metaphor of the scaffold because the scaffolds, it's very intuitive that when you build a house, you first need a lot of scaffolds to support the house. And while you construct this house, the more you move forward in the construction process, the more you remove the scaffolds. And if you did the job correctly, then at the end, you remove all of the scaffolds and you have a house standing on its own. And I like to see the skill transfer problem in the same way. So we first have a robot, it doesn't know much about the task. So at the beginning, we might need to support it quite a lot. It can be to provide several demonstrations, to monitor the learning progress, to change the configuration so that we can verify if the robot has understood what's the essential information behind the demonstration. So if it can generalize and adapt the task to new situation. So here it's more of a scaffolding process. So I don't like this idea that machine learning is we collect data or the data maybe are already here. We train a model and later we execute what has been learned. It's actually much more of a bilateral process, especially if we want to make it efficient and by considering frugal learning techniques. So, yeah, are there any questions so far?
I have many. I don't know whether you're ready for them now. What you were just saying about scaffolding, that is an expression you have for roboticians and what they do in trying to design robots and to teach robots. I want to ask you maybe to speculate. After all, human beings who are sort of the most the organisms of the greatest interest in this context, okay, in cognitive science, they evolved for, depending on where you say they began, but whatever, along their lineage, there was an awful lot of evolution going on from organism to organism and species to species. I want to ask you, before we get to the most central interest for cognitive science, which is linguistic cognitive capacities, when we're still among species that are simply robots learning to do things in the world, do you see scaffolding as one of the things that happen in evolution? And if so, how does it go?
Yeah, that's an important question. So the way I see it is currently robots are missing a lot of know-how, you know, like as way to learn and the way to acquire skills. And the impression I have is that we know a bit how to do it, either at very low level, at really like I would say like movement as a trajectory that we replicate, or at a very symbolic level, so very, very high level, where here we would have a task being described more as a sequence of very high-level bricks. And here, this high level, we often have the language that will be associated to it. Because of these high-level bricks, we can associate words, and we can start to explain what we do, because we have a better way to phrase what we are doing. And in between, we have a lot of things missing. So we in some way, it's not that we go from low level to high level. I would say we go in both directions, but there is in between a lot of things, a lot of components that are missing and that are also hard to connect. So this, I think we can also see that if we look at the different research areas that each group is specializing about. You will find quite a lot of groups specialized in one or the other, but rarely encapsulating the whole spectrum. And I think it's because it's a quite complex problem to understand how we can link the two, because it's also like covering a very wide range of research from sensorimotor control up to higher level mechanisms of cognition.
Part I missed is the scaffolding.
So the scaffolding is like for us, like what it encompasses is I would say to set the task specification. So how much can we help the robot? You know, many people will not put any scaffolds and will say it's reinforcement learning. We have a robot that learns on its own, and we give a very, like high-level view in the form of a reward function, and we let the robot try to discover on its own. On the other side, you have system where the user is doing nearly everything, in the sense that if there is a new problem, you have the user behind showing a new demonstration. So you have on the other side system that are too heavily relying on users. And this notion of scaffold is to show that ideally we would like this amount of support to be considered in a dynamic fashion. So not to fix it too early, but to make it evolve depending on what the robot knows or what the robot can produce as skillful behavior. And to make it, so often it's going from a lot of support up to no support. No support means an autonomous robot, autonomous system. In reality, it's not going only in one direction. A bit in the same way as a house, maybe we remove too early the scaffolds, and we see that one wall is not standing very well, so we will put back the scaffold. So this process is a bit more dynamic, I would say. Like it depends on what we observe as the execution of the robot. So it means the user needs also to understand what's the level of skills of the robot, which humans are also quite good at, because we are used to have this kind of assessment about the others. So we can also naturally map it to the robot. So if we observe a robot, we can actually judge, I would say, the robot quite easily. So if it fails, we understand. I mean, we can assess more easily than the robot itself, because sometimes we have systems that are completely off. Like you have a robot transporting a mug full of water, then the robot could drop the mug in between, and you would have a system continuing as if nothing would happen. And you have system like that where the user can much more easily assess the level of skill of the robot rather than the robot itself. So to me, it's the way I see the notion of scaffold. It's to better understand what the robot can do on its own, what the user can do to help the transfer of task, in which way the user can help. It might be multiple users. This image is also showing that some users might know part of the task, some others might know other parts of the task. The demonstrations can be of different quality. So ideally, we would like a robot to also be able to assess this. So not to use demonstrations all as equal demonstrations, but to associate in some way some kind of weighting or some kind of cost or reward to all of these demonstrations. And the robot can ideally learn from various quality of demonstrations. So sometimes there are many people talking in robotics about failed attempt and successful attempt. So it's like taking a dichotomy, like saying in the whole range of demonstrations, I will make one cluster as bad demonstration and one cluster as good demonstrations. And I will try to use these two clusters as a way for the robot to understand what is good, what is bad. In reality, for many tasks that we have, the resolution is it's much of a finer resolution, in the sense that we could put a cluster in the middle that is average demonstrations. And if you continue this reasoning, you can actually have a continuous stream of quality of demonstrations. And in my view, ideally, if we associate some kind of, I would say, score, or some kind of weight to these different demonstrations, then we could have robots that could exploit a large range of demonstrations of different quality. So the ideally a robot could understand this person will provide demonstrations of high quality for this part of the task, and this other person will provide demonstrations of high quality for another part of the task. But it's something that is really like putting that in practice as models within a robot is more like research perspectives, but it's very hard to consider all of these elements in practice when we transfer
Okay,
stuff.
I'd like to invite David Strohmeyer, who's actually the next speaker in the series, but this is the end of December and his will be in January, to start thinking now, because I'd like to make some connection between the kind of thing that you're going to be doing, David, and what has been done today. I found Sylvain's presentation extremely lucid, and I found the demonstrations extremely suggestive. And they touch so many things that happen in this series. I don't want to monopolize this. I just tried to touch on a few joining points, but I really want the people who are here now to prepare their own interventions. En avez-vous d'abord en français? Non, je vous donne quelques minutes parce que j'en ai plein. Okay, so one major one, and I mentioned it in connection. You?
I have one question, yes.
Okay, why not?
Well, it was mostly related to the
Loud.
sorry, it was mostly related to the observational learning, because humans are able to learn through observation because we have those mirror neurons capacities, but it is because we share like the same type of body. And you said that one of the limitations was because when humans move, maybe they are using more space. So I thought maybe the problem was not with the observational learning itself, but is it maybe with the robot's body instead of making it more similar to a human's body than just putting it all the way together.
Yeah, it's an excellent point. I can actually, yeah, I can show that with the next slide. It's a slide borrowed from ethology, so the field of ethology. And here, this experiment is actually showing. So first, it's showing that there is a difference between goal level emulation and action level imitation. And I think your question is exactly related to this, in the sense that if we would use only action level imitation, then if the robot has to copy what it's observing, then it could use only, if the action is not possible, then the robot would not be able to replicate this action. Instead, if the robot would have this capability of understanding what's the goal behind the action produced by the user, then here the robot could find in some way its own way of replicating the same goal. So in terms of workspace, it might be, I can maybe reuse the example of a tool that I had before, you know, this ratchet that could be used to bring back objects that would be too far away. Then we could typically have the user demonstrating some task and maybe using a large part of the workspace, and having later a robot being, let's say, skilled enough to understand that if it cannot reach the same workspace, it can use an object to compensate for these differences between the user's body and its own body. And yeah, so I think it's a very good question. Like, if we would have this ideal mechanism that would be able to use the demonstrations in both ways, as action level imitation and goal level emulation, then we would indeed not need to care too much about the difference of bodies and embodiment between the demonstrator and the imitator. And these studies, like, they are for us like highly inspiring as way to determine what needs to be learned, how to use the demonstrations. And also it's informative to know that it's not only one being better than the other. You know, maybe so it would be wrong to think that we need only goal level emulation. Because behind the action, what is nice as a mechanism is if you copy the actions without understanding the goal, you can still copy the action. So you are not limited to a transfer process with things that you understand. So copying the action, this kind of blind copying of the action, can be very useful in order to later reach like making tasks that are much more elaborated, because you first don't understand the whole concept behind, but by having these different actions being learned, then usually like sequencing these different actions will allow to reach goals that are more elaborated than if you would not try to replicate what we observe. And these studies are here with chimpanzees and human infants are really like yeah, for us a way to understand what we should how we should make these two levels of imitation be exploited. Because here in this specific experiment, what's happening is there is this box, so it's a puzzle box with different steps that needs to be taken in order to open the box. On some of these steps, it's complicated mechanism. So since it's a sequence of actions not being not being obvious, then if you only do goal level emulation, then you have a problem to open this box. While if you if you imitate action level without thinking too much, but imitating what's the actions that have been performed by the demonstrator, then here you can open the box. So if you trust, there is also this notion of trust. Here there is also like a lot of social interaction, because here it will depend a lot in this kind of context, like who is interacting with. But if the child is trusting the demonstrator, then the child will even replicate actions that are useless, but he will still open the box in this case. So even if here some part of the actions demonstrated by the caregiver is completely meaningless, blindly copying here will still fulfill the task. So here there are also like a lot of things that can be discussed as a possible mechanism to craft, for example, tools that would be more elaborated. So we don't know yet what the tools will be used for. We don't know yet when we will use the tools, but it's a way by copying to craft to craft techniques that can later on be seen as successful. So in some way we have a similar kind of problem, but very technologically driven this time in robotics, is to know what should we copy. Is it the goal that we detected, or is it the actions that we have observed? And I think your question is making a lot of sense. As observational learning, we could ideally infer both aspects from these observations.
Well, Amy, do you have a follow-up, or are you satisfied?
I think I'm mostly satisfied, yes.
You touched on some other extremely controversial issues in this series, not usually in connection with robotics, but in connection with large language models and in general language models, where the field is, I can't give statistics, but it's definitely divided on the question of whether it's appropriate to say that these large language models understand anything at all. And you used that controversial word when you were talking about robots. Did you mean it?
So here I would say I selected slides that I know would raise debate, because I know what you are interested in. So I have other parts of my presentation that are quite different, but I wanted to insist on this slide because I guess it was maybe the most important to make this link, so that we can maybe discuss like the way we see that as roboticists on some things that we might not that we don't understand fully as well on our side. So for us it's more inspiration more than knowing the topic very well. So so I'm happy to also know your opinion about this and to have your feedback.
Well, no, it's not my opinion. There are actual animal data. You talked about that little mammal on the left, the human. You didn't. It's also true about the little mammal on the right, that if you put them in a situation where you sort of train them or let them know that what you want them to do is to imitate your movements, they will imitate your movements, both the little mammal on the left and the little mammal on the right. And if in the process of doing this imitation of movement exercise, you in fact, this is a well-known example with the child. If you're making it doing a reach, okay, you're reaching like this with your hand, and the monkey or the chimpanzee or the child in this paradigm is imitating what you're doing. But at one point you do it, I don't know if I can do this right. Your screen, and I reach forward like this, but I actually act as if I'm not quite able to touch the screen. It immediately drops the paradigm and it brings you the screen, because it does know why you're doing it, what you're really trying to do, and not just a raw imitation. those two components, they are there in what you were just speaking about a few moments ago. But my challenging or controversial question is, surely these simple robots, it's not present there in the form of an understanding. We're talking about something else that they know how to do. And know-how is not psychological, it's just they know how to do that. It needs to be done. It's not understanding. And it touches on the same controversial question with LLMs.
Yeah, I see your point. Also, there is a similarity, also controversial, I would say, for robotics, but more at, I would say, algorithmic level, is that there are two broad ways of having a system that will use demonstration and replicate this demonstration. So it's either we think of it, I would say, at trajectory level, where we try to replicate a trajectory. And when this trajectory can be a bit smarter, it can have some adaptation aspect. And another way is to think of this as cost functions. So it's more like I would say, optimization and optimal control view, that we have a cost function, and we would like to minimize this cost function, and now we need to find a way to minimize it. So we need to find actions or to build our own trajectory that would minimize this cost function. And it's often called like optimal control. We find a controller that will optimize for this cost function. And groups of researchers who focus more on this optimal control aspect, they will tend to think of imitation as an inverse optimal control problem. And by inverse optimal control problem, it means that they would like now to estimate what's the cost function based on the demonstrations. And often this view, this very like a programmatic view, I would say, of the problem, is already showing that depending on the tools that we have, then we will either tend to think of the learning from demonstration as something that is related to goal level emulation, because if we want to infer a cost, it's really like trying to understand what was the goal behind. So it's like technically what it corresponds to. So it means this cost function, we have maybe several components, and we need to understand, we have to do that. Some part can be more, can be different weighting terms. So the demonstration would be here to find the structure of this cost function, while the first group of researchers would be doing more like trajectory level, then we will think more of the actions as really like a sequence of low-level control command that needs to be replicated without necessarily understanding the whole, the overall goal of this trajectory or this movement. So even if there is not the large language model aspect, there is already this kind of dual view that we have between people like doing like control on robotics. It's either to pass through a cost function or to treat it as data to replicate. And and I think there are some interesting mappings also with the study of LLMs.
I don't know whether goal level, trajectory level dichotomy is deep enough and universal enough to get very far with it, but I think it's a start, and it shows an aspect of research in robotics that is wrongly and unfairly rejected as being just building gadgets that are useful for people. On the contrary, there are some more fundamental questions there, even pointing in the direction of what it means to understand something. I mean, all of our prior evolution as mammals was in the area of robotics. These are robotic capacities on which eventually language capacities were built. And I think we are, I mean, I'm extremely hopeful and admiring of the work that's coming out of robotics. I think the roboticians, perhaps not you, have not thought of their work as being quite as fundamental as it really is in cognition. It is. We are mostly robots that do the stuff that your robots do. And the way you're working with them, right, it's partly motivated, of course, by building gadgets that are useful for humans. But you are running into fundamental things, and even this simple distinction between goal level and trajectory level is that sort of thing. That's more like that's a comment rather than a question. I'd like maybe it's just my dream there. I'm inviting roboticians a lot to this series, and some of the people who are interested in high-level cognition and language are perplexed about why is it we have so much robotics forced on us. I think it needs to be forced because it was forced on the entire species for hundreds of millions of years. Anyway, David, are you ready to join in, or did you just turn on your machine and fall asleep? David Strohmeyer. Just in general, for those who are here.
Can you hear me?
Yes.
Can you hear me?
Go ahead.
Yeah, no, I did not fall asleep. I'm on my phone, so I'm a little bit fiddling around with permissions and stuff to even talk. But yeah, I did find that what you said about understanding quite interesting and relevant to a little. Yeah, I think I want to talk. I'm going to talk more about this after Christmas when it's my turn. I'm going to probably do more on the philosophical side there. So I do wonder there whether there's one sense of understanding involved in like roboticist goal achievement, and when you talk about language understanding, right? That seems like a very well, that seems contentious, even though what I'm going to say is probably in line with it is actually the same. But yeah, that's just the thought that occurred to me when we just talked about it.
Sorry to put you on the spot like that, but we're about
to
bridge 2 years in between now and January. So I thought we have to make a direct connection there. Now I'm inviting other people. You're allowed to ask your questions in English or in French. We have one. Tu veux le faire en anglais ou en français?
Bon, je vais le faire en français pour le plaisir.
Vas-y. Can I ask you, Sylvain, when this question is asked, could you, before answering it, could you translate it into English and answer in English? Okay, vas-y.
Oui, bonjour. Merci d'être là avec nous aujourd'hui. Super intéressant. Je me demandais en termes, vous parlez beaucoup de learning, d'apprentissage, et on voit beaucoup imitation, tout ça, mais vous n'êtes pas sans savoir qu'en termes de robotique, il y a toujours la même critique sur la profondeur du raisonnement. Et puis la prise en charge de la pragmatique, de l'attention, d'un modèle du monde, d'une théorie de l'esprit. Est-ce qu'il y a des intentions dans vos futurs travaux d'aller enrober le côté mécanisme d'imitation qu'on a vu d'une profondeur de raisonnement, on va dire? Je sais que vous avez dit qu'on n'est pas là en train d'imiter le raisonnement humain, mais ça pourrait être intéressant selon vous. Comment vous voyez ça en fait?
Merci pour la question. So yeah, the question is is that often like with robotics, like we tend to see systems that are not really having like a high level of reasoning. So there is often like examples that are far from a theory of mind, and that are like more like making, I would say, simple task and not really doing that with a higher level of cognition. I would say I would tone down this a bit. I would say more that the problem is the gap between the low level and the high level. So there are still like groups of researchers in robotics who will focus on this higher level cognitive aspect. But sometimes in this case, the robot is sometimes it's arguable if we really need the robot. In some of these examples, while you have also many other researchers who will focus only on the low-level component. And here it's also disputable to that if you focus only on this low-level component, then you cannot make this bridge between the high-level component, higher level components. So I think that one of the main challenge in robotics would be to but we need these two levels, I would argue, to make the problem, really the interesting problem to be tackled. But it's very tough, so it's very challenging because it's a range of know-how that is very large. But the way I see it is that it's here that you would have the most interesting problems to be tackled. And unfortunately, in practice, there is this gap where it's either we tend to make it maybe too high-level cognition, but ignoring the robot, or too low-level control and ignoring that there are smart ways of gathering these different controllers and orchestrating these different controllers so that the robot can produce some behavior that is not only a pick and place, but that is a higher form of reasoning. So it's a personal view on. Yeah. Did I answer your question? Est-ce que j'ai répondu à votre question?
Oui, donc ce que je comprends, c'est qu'en fait, c'est pas l'intention qui manquerait, mais c'est d'autres chercheurs qui s'occupent de ce côté-là. Mais ça serait intéressant de voir l'interdisciplinarité des deux résultats de recherche éventuellement.
Tout à fait d'accord.
Si c'est dur, parce qu'on voit pas de causalité, on voit pas tout ça.
Oui.
Mais je vous entends. J'avais une autre question, mais je suis pas sûre que ça a un rapport direct avec la présentation, mais plus vos écrits qu'on avait comme lecture sur le dual learning humain-machine dans les deux sens versus l'éthique, la gouvernance de la chose, qui est sécurité, tout ça. Est-ce qu'il y a comment on contrôle ça quand il y a un apprentissage bidirectionnel? Comment ça fonctionne?
So it's another very important question. So the question is to know, like with these different mechanisms that I described, like how can we guarantee safety, and how can we guarantee ethics, like how is it considered in these different mechanisms? And I presented this kind, I would say, of broad range of techniques that we can use. Here, I think that here the role of models being interpretable is, in my view, very important decision to take, because we have really a range of models. Some will be interpretable, some will not. They will all achieve very good results, but what we can get with the interpretable model is an easier way of generating a mechanism for safety measures, typically, because if we can understand what is in the box, then we can know much better what to do out of it as a safety layer. But it's not always possible, because some of these techniques, like there are a lot of structures, especially with neural network. For us, it's mostly with vision, where we don't have the full details about what's happening. So what we try to do in our work is still to segment a bit what we can do with perception and to try to limit what cannot be interpretable as a structure. So that we can keep what is I would say, a trajectory level, and what's the plan, and what the trajectories of the robot. We can keep control about what the system is generating, so that we can put a safety measure on that. But it's again like another full field of research. So it's to come back to the previous question. It's also that ideally we would need all of these different bricks, but it's so many components to work together that it's rare that you can find research groups having the full spectrum of all of this know-how. So it's more like people who need to work together, but also like I would say having representations and models that are compatible with what each of these fields of research require.
Okay.
Je vous entends, super intéressant. Encore une fois, ça revient à l'interdisciplinarité. Ça me rappelle un séminaire qu'on a eu en robotique aussi, où on parlait d'humanoïdes qui étaient déjà vendus. Puis j'aurais pris votre opinion là-dessus, dans des magasins, alors que le côté cybersécurité sur les données vidéo open source n'était pas géré, en fait. C'est un enjeu, comme vous dites, encore à gérer. C'est quand même dangereux des fois de partir avec de la robotique commercialisée sans les enjeux interdisciplinaires abordés, non?
Je suis tout à fait d'accord. So the question is to know, like we see on the market currently, like humanoid robots being available for purchase, and sometimes these robots can collect like quite a lot of data, and sometimes it's not super clear how these data are used. Yeah. And yeah, so one of the yeah one of the question is is to know like is it a technology, like sometimes we are scared about an object like a phone, and when we have a humanoid, because maybe of the humanoid form, like what does it involve? So it's important, like questions to address. I'm not an expert in this, but I know that technologically, yes, it's a machine that can collect data, and since it's a physical machine, it's even worse than some of the mobile devices that we use, because it's something that is actually physically moving. So it's like actively perceiving the data. So I think, yeah, there are questions like that needs to be addressed, and to try to see if technologically there are ways to still use like different modalities, including vision, so that the robot can do its task, but still having some mechanism so that there is protection about the data being collected, and also like having, like I would say, standards being put in practice, so that we know exactly when we buy a robot that we have this kind of privacy standard being used.
Si.
Okay, we're running out of time. We have time for one other question that will not require a translation. Go ahead. Yes.
Thank you for the presentation. Actually, my question is related to the safety perspective, as it's the main concern that nowadays, once we hear about robotics in general, the big concern is about the safety, and especially with robotics that have been used for assistive tasks, like helping elderly people to do some things, or the task that needs to make movement, for example, like in the restaurant, hot drinks or cold drinks. So my question is about how do you enable active exploration and learning from demonstration while ensuring safety and comfort in close human-robot interaction, especially in assistive robotics?
Yeah, thanks a lot for the question. Indeed, it's something I didn't touch yet in this presentation. So just to let you know, I had many other slides, but I think that yeah, the topics of discussions here are excellent. So I will not show all of the slides I prepared, but this one I think is important. Like we have robots that can be controlled in the force domain. So it's not the case for all robots, but there are like two kind of categories of robots. One category is position controlled. So here we give commands that are really like moving in space, and we have a robot that can be stiff, like it will be stiffly moving to a desired configuration. And the force control robot, what we can do is we can change the level of stiffness that they have. So we can have a compliant robot that will be soft if we want it to be soft. The extreme case is what I demonstrated with kinesthetic teaching. Here we have a robot that is so soft that I can move it in space without feeling its weight. So here that's the extreme case where I have like a robot not stiff at all. It's gravity compensated. I can move it everywhere. But in reality, what we can do is to view the interaction with the persons, like the physical contact with the person, as some kind of virtual spring that would be connected between the robot and between some kind of virtual target that the robot has to reach. And if we think of the controller as a virtual spring, it means that we can change the stiffness of this spring and we can change the location of this spring. And it's often this kind of techniques that are used for physical human-robot collaboration. We don't need to learn, we are not only learning a trajectory, we are also learning a stiffness profile. And the stiffness profile, it can vary in different directions in space. So to give you an example, maybe holding a cup, if I'm thinking of it as a virtual spring, if I'm holding a cup, what is important, if this cup is filled with liquid, it means that if there is a perturbation, I need to make sure that I'm not tilting the cup like that, because otherwise I would spill the liquid. But translation is fine. Like I can move it sideways. I can even rotate it in this way. And here there is no problem. So if this is translated as a virtual spring, it means that I can have a robot that is soft in some directions and that would be rigid in other directions that would have an impact on the completion of the task. And when interacting with people, it's something similar that we need to set as a learning problem. It's to understand what the task requires and all of the other dimensions that are not useful for the task, the robot should remain soft. And here it's most of the time the way we would interact with someone. If we help someone to stand, you have like someone being seated, and we would like to help the person standing, we will need some force, but not in all directions. Like we can be very compliant in some directions and apply more force in other directions. So learning also requires this. If we want to have safe robot, and it requires robots that can be controlled in force. So it's also like some kind of I would say debate in robotics. It's to understand in terms of robot platforms if we need force controlled platforms or position controlled platforms.
Thank you. Yeah, that's fine for the learning by demonstration. But my concern as a PhD student in cognitive computing, if the robot works by giving them instruction like a speech, I don't think the results will be the same. Because here we have a concern about the linguistic interpretation and the mean, like how the robot will understood what the human means about the words, because here we intersect another domain, which is the linguistic. So sometimes he cannot move the hand of the cup in the correct way to give it to the, for example, to the elder person, in terms if the learning procedure is not by reinforcement learning or learning by demonstration, it will be different aspect. So I will stop my question here because I think it's a different strategy, different perspective. So thank you.
Yeah, I fully agree. But it comes back to this point that we need to bridge the gap between this low-level component and this higher-level component, because they are not everything that we can describe with words. Like
yeah, that's my point. Is that sometimes that giving the nowadays there is a robot named Alexa. I think that you give it order to help the woman to do like housekeeping stuff, something like that. So it functions well because there is it is pre-trained by giving exactly the terminologies that are used for in this context. So you give it like a context, so it will move and do the stuff based on exactly what should say it. But if she said something else, it will not understand and she will repeat again. I didn't get the point. For example, can you please exactly repeat what you want me to do? So it will not function 100% correctly because of what exactly she learned about the robotics. If she is, we assume it like she is a housekeeper, like a robot. So yeah, so I think by language it will be a different story. This is the point.
Yeah, language is more to I would say to orchestrate the lower level bricks of and the language can be here to describe some aspect, but not all aspects. And here we are talking about forces, and I think it's a good example where it's difficult to actually explain, even like to explain what we are doing as an assistive task. It can be very complicated to do, to explain with words. And also the amount of force that we apply, we even don't know by ourselves. We have actually no idea. Like we cannot describe it easily by saying I applied a 3 Newton force on this arm in order to help the person. It's never like that. We can demonstrate easily, but we cannot put values, I would say, like a quantitative description about what we do. And here we discussed about forces, but it's also the case for other gestures. Like here in my work, it's more about manipulation tasks that are, I would say, functional tasks. But if we think of gestures, more broadly speaking, if we think about communication through gestures or even dance, like dance, it's difficult to describe a dance.
Because it touches the procedural memory. So there is no fixed things in our brain that could be explained. So as a human, we cannot explain how we drive a car. You cannot explain the way that you function with something. There is something that already we have steps in our brain, but like we categorize things, but some stuff like how to do actions, we cannot explain that. So I think if a human are not allowed to do this stuff, also robots, in my opinion, also robots are not allowed to do, because who developed the robots? We. This is
But
the
here you
point.
touch another very interesting point, but I know that today we will not have time to discuss it
Very open.
in
Perfect.
details. But the important point when we think about robot controller is which part is reactive, which part is anticipative. And often we have this I would say this option. Either we can think of controller very myopic, we don't look really into the future. It's more like state action for this state. This is the action that I want to do. So something that would be purely reactive. So it's one way to think of a controller. And another way is much more anticipative. It would be more related to planning, but it can be planning within a time window. And we need to consider what's the right size of this time window, and this needs to be dynamically changed, because with your example with the car, what's happening is when you learn driving, you will have a much more feedback loop. You will do this, like the cognitive workload will be higher because there are things where you need to cope with perturbations. And then the more you know how to drive, the more it will be fluent on the open loop, I would say. Okay, so you will not have, it will be an automatism that doesn't require this feedback to be, it will be automatized. But when you come into a new car, maybe a model a bit different or something that is not exactly the same system, then here this open loop will come back progressively, it's dynamic, like you can anticipate the dynamic way, and if it's not as expected, so if the environment is changing, you need also this time window to be modulated. And sometimes a robot, they don't do this yet, but they should do it. So currently we tend to specify this anticipation window as hard-coded, but in reality, it would be nice if we would modulate this time window according to the environment in which the robot is.
It is not at all a sign of ingratitude on my part to say that we have to end it there, because but however, I want to say as a matter of record that from many efforts to use a dialogue between the sensorimotor side of cognition and the verbal side of cognition, this one has come the closest to being successful. I know that it's because of your work, Sylvain, and your lucidity on it. So I want to thank you very much.
I'm glad you say that. Thank you again for the invitation.
Thank you. Thank you.